Okay, let's talk about how do we get to the famous p-values before we keep talking about statistical significance. I think it's important to understand p-values properly before we move there. And for this, I decided to do a whiteboarding session, see how it goes. So imagine that you have two hypotheses. So this is your hypothesis 0. So hypothesis 0. And this is your hypothesis 1. And because hypotheses are important, they are like pergaments. They are important documents, so they have to be folded. You might imagine that the hypothesis 1 is something like, I don't know, the Earth is flat. And the second one is the Earth is round. So we have two hypotheses that they contradict each other. We have status quo, so we believe that the Earth is flat, and the second hypothesis is that the Earth is rounded, meaning the Earth is a sphere. And we want to run one experiment, and we want to prove that indeed the Earth is rounded and that we are going to gather enough evidence that actually dismisses the so-called null hypothesis, meaning the Earth is flat. Okay, so now we begin to run these experiments, and the way I will do this is very simple. Say that we have experiment 1. We have run one experiment, and in this experiment we gather evidence, and when we finish gathering evidence, we end up having that this is how much evidence we have that the Earth is flat, and this is how much evidence we have that the Earth is rounded. So this is H1, this is H0. So this is the amount of data, right? So this is the amount of evidence, right? This is the evidence axis. And here we find in the first experiment that we have really low evidence that the hypothesis 0 is true. And we have a lot of evidence that the hypothesis 1, so the Earth is round, is true. So we have a lot of evidence of H1 being true, not a lot of evidence of H1 being true. Okay, so this will be all good and great, and most of the time we just run one experiment, but to understand p-values you have to go a little bit beyond that. And the way what p-values work is imagining. So you do the math, and I'm not going into the math, I'm just going to explain what is the intuition behind it. But it will be to say, well, now I will repeat this experiment a second time, right? A second time. Oh, actually, I wanted to, this is experiment and experiment number 2, right? And when I run the same experiment, I get the same result. So not so much evidence of H0, so Earth is flat, and a lot of evidence of that the Earth is being rounded. And then I keep repeating this experiment and say that we repeat experiment a number n 100 times, right? And we keep observing the same thing, right? That there's not so much evidence of the Earth being rounded, and given that the data that we gathered, that the information that we gathered, so there's a lot of evidence that the Earth should be flat. And again, the nature of the experiment, we don't know. We're going to abstract from that. But then suddenly we find one experiment. We find one experiment where actually the data links towards the hypothesis where the Earth is going to be flat, and there's not much evidence of the Earth being rounded. So this happens in the experiment I. And then we run a couple of other experiments, and then we find again the same scenario, And this is the experiment Yod. And we continue, and the vast majority of the experiments just show the opposite direction. So we end up having here H0, H1, and the experiment 100, right? Because we agree that we're going to run 100 experiments. So how many experiments we had where the evidence for, so we say that this is the evidence, call it like this, let me use a Greek symbol, so that the evidence of H0 is bigger than the evidence of H1, that the data implies that H0 is true, and therefore we have more evidence of H0 being true. Well, we find, I was one of them, so I was one of them, and Joe was one of them, and I can tell you that we had 4 of this. So we had, 4 of these cases, 4 cases. And of these 4 cases, obviously we had then 96 cases where we had the opposite. So we have more evidence of the Earth being rounded than the Earth being flat. Right? So we have 96. So it means that if we continue to run this series of experiments, we are getting a probability of 4% that the data indicates that the null hypothesis is true, and we are going to have a probability of 96% of the data indicating that, in fact, the Earth is going to be rounded. Okay? So where the p-value comes in place? Well, at the beginning of the experiment, you fix the p-value, and usually the p-value is set for many experiments at 0.05. What does this value mean? Well, it means that this is a threshold, and we say that if the probability of observing P0 is below 5%, so if this number is smaller than the p-value that we fix a priori, then we say that the hypothesis 1 is true. Which makes sense. Essentially, we're saying, you know what, we are going to believe that this experiment is solid if we observe that the evidence indicates that the Earth is flat less than the criteria that we choose, right? So it's below than this probability. And then if that's the case, so if we meet this condition, then we say, you know what, I think the Earth is rounded. If we would have found more cases, say if we would have found that this, instead of 4 cases, would have been 50 cases, right? Half of the cases. Then we have a strong suspicion that the data is not telling us that, in fact, the Earth is rounded. So we will actually believe that the Earth, we have reason to believe, given the data that we are getting, that the Earth might be, in fact, flat. So we cannot reject the original idea that we had that the Earth, was flat, this is the original idea. This is what we started with, right? And this is the idea that is challenging. So this is a challenger idea. Yeah. And this is the intuition behind the p-values. In the next video, we are going to try to understand better how this is being calculated and what errors you shouldn't avoid when you're trying to interpret the p-values.